In this video, I'm going through Pure 1, Chapter 8, and it's section 8.2, which goes through a semi-algebraic way of proving the differentiation rule. And it's kind of a proof, but it's using a mixture of numbers and algebra. It's not examined, so this video is optional. And it's very similar to the last example in 8.1. So just once again to remember that we can, instead of drawing a tangent, we can draw a chord between 2 points on the curve, and so if I call that point P like we did before, as the distance between A and P gets smaller, as that chord gets shorter, the gradient of the chord becomes closer to the value of the gradient of the tangent. And so it gives a more accurate estimate or a more accurate representation of the gradient of the curve at that particular point. And we've said that the letter H represents a very small change in the value of x. It's a very small distance away from the point A. And they've said that you can also use delta x. So this symbol, that symbol is delta. And again, it represents a very small change. So the example says the point A with coordinates 4, 16 lies on the curve with equation y equals x squared. At point A, the curve has a gradient g. And part A says, so show that g has a limit where h tends to 0. So the limit as h tends to 0 is 8 plus h. Show that the gradient at the limit as h tends to 0 is 8 plus h. Show that the final answer, basically, as h gets smaller and smaller, as the distance between A and P gets smaller and smaller, that it's practically not there, the final answer is going to be 8 plus h. That's what they're asking you to do. Okay, so we've got the first coordinate is x1, y1. The second coordinate is a small distance away. It's h distance away. So the second coordinate for x, it's going to be 4 plus h. So that's x2. And then because it's the equation, it's the curve y equals x squared, the y is found by substituting the new value for x into the equation, into x squared, to get 4 plus h squared. So 4 plus h squared is y2. So we've got our two coordinates. And the gradient, of course, is y2 minus y1, the distance in y, and it's x2 minus x1, which is the distance in x. And I'm going to go through, I'm going to substitute in, let me call it g, because that's what they've called it in this example. So y2 is 4 plus h squared, which I'm just going to write as a double bracket, minus y1. y1 is 16. Divided by x2, which is 4 plus h, take away x1, which is 4. And again, like we saw previously, 4 take away 4 is 0, so they're gone. Then I multiply out the double bracket, so I've got 4 times 4 is 16, and I've got 4h add 4h is 8h, then h times h is h squared, and I take away the 16. And again, I hope you can see, 16 take away 16 is 0, that's gone. And I'm left with 8 h plus h squared, which I can factorize. So I factorize the h out, and I get 8 plus h over h. And h divided by h is 1. So I have now shown that the gradient is in fact 8 plus a very, very small distance. But as this very small distance gets smaller and smaller, that's what it means by h tends to 0. This distance is getting smaller and smaller, it's becoming non-existent, it's becoming 0. What is the value of the gradient? Well, 8 plus 0 is 8. So the value of the gradient is going to be 8 as it gets smaller and smaller. Now, the algebraic proof, as I said, this is semi-algebraic. The algebraic proof starts, it's basically like this, but it starts with the first coordinate being xy, so that's x1, y1. The second coordinate being x plus h, and x plus h squared for y equals x squared. And you would do exactly the same thing. And what you end up with, and I'll show you, what you end up with is the actual derivative. So you remember, I hope, that if we're going to differentiate, so if we find dy over dx, we subtract, we multiply the power by the coefficient. So 2 times 1 is 2, and then we take away 1 from the power, so it becomes 2x. Well, what you end up with is that value. That's the gradient function. So we have the gradient is x plus h times x plus h, y2 minus, sorry, that's x squared, because y is x squared, minus x squared over x plus h minus x. X, take away x, gone. The gradient is going to be x squared, and it's going to be plus h squared, and then x times h is xh or hx, and then it's plus 2hx, and then minus x squared over h. Again, x squared, take away x squared is gone. I end up with 2hx plus h squared. I'm going to factorize the h out. So I'm going to get h is 2x plus h over h. These two cancel, so the gradient is going to be 2x plus h. As h gets smaller and smaller and smaller, the value of the gradient is going to be 2h, and 2h is the gradient function. So that's where I get my rule from. And if I do that with something like x cubed, or if I do, I'll get a 3x, and if I do that with something like 2x squared, I'm going to get a 4x. So that's where I get the rule from. And that is the end of this video.